Hello everyone, welcome to topic 6.5, energy of phase changes. By the end of this, you should be able to explain the changes in heat absorbed or released by a system undergoing a phase transition, so solid, liquid, gas transitions, based on the amount of the substance in moles and the molar enthalpy of the phase transition. There is technically an equation, and that is Q is equal to M delta H, or Q is equal to N, where N is moles delta H. Okay. So continuing with our notes, we can calculate the heat released or absorbed when a phase transition takes place. There is no change in temperature. The energy is used to change the position of the particles relative to one another. So in other words, the potential energy is changing, right? If you took a book from a desk and lifted it up onto a higher shelf, that is increasing the potential energy, but that takes energy to move stuff, right? So to change the potential energy or to move something further away from something else, you have to put energy into it. So to separate particles, you have to put energy into the system. Notice that the segment for boiling is much longer than the segment for melting. This is because separating liquid particles to form a gas requires more energy than separating molecules from their solid state to a liquid state. That is because the degree of separation for solid to liquid is much smaller than it is for gas to liquid to a gas. Liquid to a gas, you are having complete separation. So you have to completely overcome all of the intermolecular forces present within that substance. Whereas for a solid to a liquid transition, you just have to kind of weaken them so that the particles can flow past each other, but they're still interacting. To calculate the heat needed to perform a phase change, when a phase change occurs, we use the enthalpy for that phase change and multiply it by the amount of material. So those two equations I gave you at the beginning, where Q is heat again, and M is mass, or N is moles, and this will depend on the units of delta H. Delta H tends to have units of either kilojoules per gram or kilojoules per mole. And the kilo can be optional, but it's joules of some persuasion per gram or per mole, where this one you would use for M and this one you would use for N. Okay? If you are given grams, but are given this one, you will change grams to moles first and then perform your calculation. And vice versa. If you're given moles, but given the kilojoules per gram, change to the matching base unit before performing your calculation. Okay, so we are looking at this diagram where we see endothermic processes going across the top and exothermic processes across the bottom. Please note that endothermic processes are delta H of fusion and our delta H of vaporization, which are the ones that are used here, vaporization and fusion. These values will be positive. And then for the bottom, for exothermic ones, the delta H of fusion and the delta H of vaporizations will be negative for all of these. Okay? Please make sure you're remembering that because energy is released or absorbed based off of the type of process taking place. So let's apply these in the I do and the we do. So given the heating curve for mercury, calculate the heat to freeze 100 grams of mercury at its melting point. So we are here, okay? This is its melting point. So since it is just a phase change, we are looking at Q equals M delta H, but not really because this is in kilojoules per mole. So we actually need to change M to N, grams to moles. Okay. So doing that, first we take 100 grams of mercury and we're going to change that to moles. So 1 mole of mercury has a molar mass of 200.59 grams. So our amount of mercury is oops, and this is 100.0 because we have 4 sig figs, so 0.4985 moles of mercury. So now we can use that in our equation, and we're going to use Q equals N times the delta H of fusion. And so plugging in our N, we have 0.4985 moles times our delta H. And since we are melting something, okay, no, we are freezing something. Freezing means that this process is exothermic, which means that the sign of our delta H has to be negative because we're going to take energy out. So the 2.30 kilojoules per mole has to be negative because we are doing the exothermic process. And so when we perform this calculation, you should get negative 1.15, because 3 sig figs here, kilojoules. The moles cancel out because we are using a very specific quantity. Okay. So let's practice another one, and I'm going to help get you guys set up, and then I'm going to ask you to pause the video. So aluminum melts or freezes at 933 Kelvin. How much energy is required to freeze 2.50 moles? Okay, and we are freezing. So freezing, remember, is an exothermic process at 933 Kelvin. And they give us both the vaporization and the fusion. Okay, because you are freezing, you are going to fuse particles together. This is the melting and freezing point, delta H. So we are going to use this one. But because it is exothermic, the value of that should be negative. Okay, so using the Q equals N delta H, please pause the video and solve this for Q. Okay, so solving this, you plug in 2.50 moles for N, and the delta H, remember, since it's exothermic, it has to be negative 10.9 kilojoules per mole because we are at the freezing melting point. So we're going to use the delta H for fusion. Plugging that in, we should get negative 27.3 kilojoules. This should fit because we are freezing, so we must pull out energy, or energy must be released in order to freeze the substance, right? Okay, so using these concepts, you are going to answer the You Do questions. Check your work, and thank you for tuning in.